the last two discussions were about harm to the DNS potentially inflicted by bad guys and also misconfigured networks. What Jim's about to talk about is how to avoid self-inflicted damage to the DNS by the DNS itself. And I'll declare an interest in this work because the organization that funds most of my time, DNSOARC, was involved in the study that Jim's about to present. But basically, Jim is going to present an overview of summary of work that he has done over the past year or more on the name collision problem.
Thanks very much, Keith. As you said, this is a talk that summarises actually two discrete pieces of work that I did over the last 9 months or so. The first of those was part of a project that was funded by ICANN to assess potential impact of name collisions in the context of new gTLDs. And the second one, there was an analysis after ICANN came up with a risk mitigation strategy about certain pieces of data which had possibly been overlooked and the potential damage that they might cause. So, where did this all start? Well, as you all know, ICANN, in its infinite wisdom, decided let there be bazillions of new gTLDs. And whenever this was first announced, there were lots of concerns about the possibility that some of those names and strings were already being used on the internet already. So ICANN had a sort of last-minute panic to say, look, we better get some hard data on this. There's some anecdotal evidence, but really nobody knows, is there a problem? And if so, what is the extent of it? So ICANN decided to commission a study in the middle of May last year to report by July of that year to try and find out, is there a problem? How big is it? And what kind of risk mitigation strategies could be used? So this was quite tough to do. And it was also very challenging because we knew at the outset that whatever findings we produced in this particular study, people were going to complain, people were going to scream, the numbers were going to be questioned and argued about and all the rest of it. So it was a little bit of a high-profile exercise. The first problem was finding data. Where could we get information? Well, one of my colleagues in the project was looking at the issues around about certificates, but we were primarily focusing, at least my part of the project was primarily focusing on queries. And we were trying to find out where we could get access to query data, and it turned out pretty quickly the only viable source of data we could get was the day in the life of the internet PCAP files held at DNSOARC, the organisation that keeps Keith in a job most of the time. So the root server operators contribute DITL files or PCAP files to OARC for each year, which essentially are complete copies of all the packets in and out from each of the name servers, all of their Anycast nodes as well. Not all of the root servers contribute to this data. But for example, when we started this exercise, there was 6 terabytes of PCAP data for 2012. And while this analysis was in progress, the DITL data for 2013 was being gathered and being transferred to the root server operators, from the root server operators to the systems at DNSOARC. And just to give you an idea of the kind of scale of that particular problem is it was taking the root server operators round about 1 week of elapsed time to physically transfer that data across to OARC servers in California. At the first look at the OARC resources that were available to me at that time, there was one very, very small, feeble little box. And it looked as if it was going to take well over 2 weeks to go through the DITL data. And this was just far too long because we knew we were going to have to make several passes of it. There wasn't enough elapsed time. As luck would have it, there was a spare 8-core box belonging to CADA, and they kindly donated that or made it available to me for the duration of this exercise. That run a very old version of FreeBSD. That had some other impacts and things. But the nice thing about that was we knew we could get through the data runs in about a week of elapsed time across all the 8 cores simultaneously. So essentially, one run of the data set was essentially 2 CPU months. A nice side effect of this, at the end of this particular exercise, was OARC got some nice new shiny boxes, and the new hardware we've got is great. You can actually do a complete run over the data set in about 15 hours. So what were the choices? One of the things we got was a great tool called PacketQ, which comes from NetNode and IIS, the Swedish TLD registry. And this has got an SQL-like language for going through PCAP files and counting things, number of packets of a particular query type, the query name, source address, all that kind of thing. Wasn't very good for doing label position analysis though. And then to try and do that position analysis for things like what were the second level strings in the query patterns that were of interest, I was then forced to use a combination of awk, TCP dump and fgrep. I actually quite like awk, so there we go. So the general idea was to take each of those 250,000 PCAP files, chop them up into 8 equal chunks and throw them across all the 8 cores and just keep going. Bang, 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 don't stop, don't go back, keep on going. If you find any kind of problems or error cases, you could then go back and then run the scripts by hand over an individual PCAP file to deal with any anomalies that might have cropped up. Just had to keep on going. There were also no locking or synchronizations issues at all. It was essentially one input file, one output file for each data run. So why didn't we use stuff like Perl or Python or whatever? Well, the reason for that was the Kira system had old versions of those very popular tool sets on them. But the very latest version of all the DNS tools that were based around Python and all the rest of it were incompatible with the versions of those Perl and Python installations that were on the Kira box. Now, the Kira box wasn't mine, so I couldn't necessarily mess around with all that stuff. And when I started to look at this kind of stuff, I ended up getting into all the usual autoconf dependency hell, because if you were to install Python, then you needed a module which depended on some other Python stuff being put in, and this was just never going to terminate in any reasonable amount of time, and I didn't have that time. So I made a quick, rapid, snap decision to say, to hell with all that, I'm going to stick with known proven tools which will get some data out of there in a finite known amount of time, and I'm not going to have to worry about anything else. The only exception to that was we had to get an up-to-date version of G++, so in order to compile packet queue, and the system administrator at Kira kindly installed that for me. So the reality was I couldn't, to use a Scottish word, blooter anything that was already on the box. Blooter means to kick something with great force. So I couldn't do any damage to any of the existing system software on that box. I had to pretty much leave it alone. And then, of course, there were other researchers who would be using that box in the future, and if I messed around with the system software, that might have effects on other research and the people that were actually so kind to donate the box to me. Why didn't we use a database? Well, similar kind of thing. There were too many unknowns. How long would it take to actually populate the data with database? How would you scale the data into the database? How would you scale the tables? What about any locking and synchronization issues? How long would it take an SQL query to run over these potentially huge data sets? And of course, what happens if that database gets corrupted in some way? So we did the analysis. We found out that essentially we could split things out in terms of a query pattern into essentially 3 categories. There were a small number of TLDs that had very, very high query rates. Most of them were in a sort of intermediate range, and there were quite a lot that had very little in the way of traffic. But the reality was pretty much all of the new proposed TLDs were already being found in the DNS traffic. The biggest concerns of all, in some respects, were for .home and .corp. The DNS traffic levels for them on the internet are greater than just about any of the existing TLDs on the internet just now. The only ones that were actually bigger in terms of traffic levels than home and corp were, for example, COM, NET, ARPA, DE and UK, I think were pretty much it. The also funny thing was that all that traffic was coming from all over the place. It wasn't localized, so we couldn't say, well, all this traffic for .foo is coming from a /24 in Singapore or anything like that. The traffic was coming from all over the place. And these power law distributions meant you tend to find there were some patterns where very high amount of data for some things, and then it would all tail off, and there was a very long tail. Another one of the nasties that was actually mentioned in passing in Kathy's talk was this Chrome random query string pattern. So Chrome has got this feature to try and detect if there's NX domain rewriting going on by the local resolving server. And the way it does is it generates a random 10-character string which used only once. So, and if that string is then queries for and comes back with something other than NX domain, you know you've got somebody doing NX domain rewriting. And the nasty thing about that for us in terms of the root server traffic, we found billions and billions and billions of these single character or unique strings of 10 characters long. And I had to count them all because I didn't know if one of these would actually turn up, hundreds of times or thousands of times. So you're trying to index or count these things, you just had to count them all. So there was a huge, very, very long tail. There were also some other interesting stuff that popped up. We saw examples of patterns that looked as if it was leakage from either Bonjour and from Active Directory. And what would happen if those things were getting NX domain responses, if that then changed to a referral response? We even saw some dynamic updates coming to the root. And there were also queries for MX records and SRV records. And the MX record and SRV records are things that particularly would be a concern, because that points to someone has configured software to go and look for these things. So why is that going on? But ICANN decided not to bother with that. And essentially they just took the approach as, well, ICANN's decision was we will essentially say that .home and .com, .corp would be considered very high risk. There's another bunch of intermediate risks, and then they said if the query rate was less than the query rate for the .bv and .sj CC-TLDs, that new gTLD string was considered safe, in inverted commas. The BV and SJ domains are completely empty, they're not used for anything, and no one's really got a legitimate reason for querying them. But they still get something of the order of 50,000 queries per day, according to the DITL datasets. So you can think of that as being almost like the background noise level of the internet. So anything that was below that, you could probably consider as not worth worrying about. However, these are not the only metrics, but those were the ones that ICANN chose. So ICANN's risk mitigating strategy was to say, right, home and corp, they're essentially dead. They've been pushed out to long grass. I think the official line is they will be released at such times as we can be convinced they're not going to cause any breakage. Other gTLDs can produce the delegation. If you're in the low risk category, off you go. If you're in this middle range category, what you're supposed to then do is block the second level names that are specific to your TLD that was found in the DITL data. So in that case, those strings will be certified with NX domain responses, and for everything else, you issue a wildcard for 90 days after the gTLD is activated. So if somebody then looks up some random string.new TLD, you should get back a response that tells them you've got your broken DNS because you shouldn't have been querying for that stuff just now. Maybe you might want to fix it. So ICANN's idea then is, the pattern is you make a query for one of these SLD.gTLD strings, you're still going to get back an NX domain response like the root server system does just now, so therefore everything's fine. That was ICANN's rationale. However, life's not like that. Because as we know, what really happens is there's an intermediate resolving server in place for a lookup. So at the moment, what would happen is a query would start from some stub client, go to the local resolving server, the local resolving server queries the root turns back with an NX-1 response, which then gets returned back to the client. Everybody's happy. Now, after that's delegated, the root server, instead of returning, of course, that NX domain response, returns a referral to the resolving server that says, go and query the new TLD servers. The new gTLD servers return NX domain, and again, life is happy. But what if we've got other stuff that queries the root server systems directly? What happens to those guys is, at the moment, they still get an NX domain response, but after the TLD has been delegated, the root server returns a referral response instead of an NX domain, and something bad might happen. So what would these, example of these naive clients? Well, that would be things like stub resolvers, proxies, forwarding only name servers, CPE crapware, all the usual kind of things we all know about. And what are they going to do when they get a referral response? Because they just don't know how to handle them. In some cases, they don't have the software to deal with it. In other cases, they're getting back information that they don't know what to deal with. Will the software crash? Will it fail? Will it give up? Will it try to do something else? Who knows? So how often does that occur? And is it a problem or not? So this was the second piece of work that I did earlier this year, and it was presented at the VeriSign name collision workshop that was run just after the last ITF meeting back in March or thereabouts. So in actual fact, to do that exercise, I went through 10 terabytes of DITL data, and this was actually 250 billion queries. So rather than just doing it for 2012 and 2013 for the initial name collision study work, this was looking at all the DITL data from all of the contributing root servers since the DITL exercise started back in 2006, 2007. And we made 3 passes. I made 3 passes over that data, doing a qualitative, comparative and historical and qualitative analysis. Woo. So, what is the extent of the problem? Well, in actual fact, there's a hell of a lot of traffic going to the root server just now that's got the RD bit set. So it's round about 12% of the total of the root server traffic is coming from things that are saying is, I can't do recursion. So this is coming from things that should not be querying an authoritative server. None of the queries that we're seeing had the RE bit set, which is a good thing because that should only be coming from authoritative servers when they send a response back, whether recursion is available or not. Where are all those RD1 queries coming from? Well, most of them are coming from the usual suspects, ComNet, ARPA, org, UK and all the rest of it. Very, very few of the new gTLD strings that we found in the DTL data set had the RD1 bit set. And by far the biggest of those, in terms of number of queries, was home and corp, and we already know that those two TLDs are essentially dead. For most of the others, there was essentially none of that traffic at all, and even when the traffic was found, it was usually at least 1 or 2 orders of magnitude, and in many cases, 3 or 4 orders of magnitude less than you'd actually find for existing TLDs. Google seems to be getting more than its fair share. I also looked at this from a historical perspective to see, has this pattern of RD1 bit setting, has it changed over the years? Have the TLDs that have been affected by it, are they changing from year to year? And broadly speaking, all of that stuff was pretty much static. So here we have some really bad clumsy graphs that shows on the y-axis the number of queries in billions and the TLDs, or the query patterns where the RD1 bits were set. You can see there was a spike in 2010, and I think this was primarily due to a DDoS attack that was going on that year. But broadly speaking, okay, there's some fluctuation, but it's relatively static and flat. We then looked at that pattern for existing TLDs, and again, there's a huge big spike in 2010, and that was for Dotcom. But we're still looking, in this case, we're talking of the order of a maximum of 8 billion queries. Yeah. And then taking out Dotcom from that picture to try and see if we can make a little bit more clarity about all this kind of thing, we still see that broadly speaking, the numbers are relatively flat. There's a little bit of a spike there for one TLD. I can't see which one that was here. I think it was UK. But broadly speaking, we're still seeing the same idea as the number of queries are relatively flat year after year after year, and the position of each TLD in that pattern doesn't seem to change all that much. The pattern for each TLD seems to be pretty much the same across all the years. As far as the rates for new gTLD is concerned, we can see things are a bit more spiky here. But the thing to notice here is the actual request counts. The maximum highest number of request counts here was 70,000. On the previous one, we were talking in billions. Now we're talking the order of thousands. So there's very little of this traffic pattern going on as far as the gTLDs are concerned. So trying to do any kind of qualitative analysis of this is something that could go on forever and ever and ever. So I made the decision to look at some of the most glaringly obviously outliers, because you just couldn't possibly try and make sense of all of this for everything. And the answer is there's nothing important to see here, just move along. So looking at some examples for 2013, we found out there were 50,000 of these bogus queries, I would call them bogus queries, for .google. Pretty much all of those 50,000 came from one school in California. Similar kind of pattern for State Farm, the US insurance company. The rest of those had RFC1918 addresses. So how could you possibly analyse where they came from? And why are RFC1918 addresses getting carried over the internet? This is again something that shouldn't be happening. For 2012, Google had a large number of, relatively speaking, a large number of diverse lookups, around about 600 queries each, coming from around 600/24s, again scattered all over the place, no direct pattern we could attribute it to one particular source. And again, some RFC 1918 addresses. And again, the general pattern was something where a suffix had been left off the TLD, so it was usually gmail-smtp-something.google rather than google.com or google.co.uk or whatever. So I suspect that was probably some kind of transient stub resolver or mail server misconfiguration that was responsible for that. Here's another that's a little bit wacky. The wackiness of the data stream that you find in those PCAP files, there's all sorts of bizarre and strange stuff going in there. And this was an example of one of the query strings that was found for .anz. And I don't think that's got anything to do with the Australia and New Zealand bank. Maybe it is. But there's a strange mixture of languages in there. I'm not even sure I can identify what those words actually are. Rosmaregi, what on earth is that? No idea. In 2008, there was a bit of traffic again for .mail, but again the pattern there was a few hundred queries spread over a few hundred /24s. How can you make sense of that? And how could you then go back to someone and say, could you please account for those few hundred queries that was made 6 years ago? Would anybody have log data for that? Would anybody be able to explain that? And again, it's a tiny amount of traffic, so why worry about it? Here's another one which I really liked. There were 60,000 queries for Klingon.site. They all had the same query ID, port number, and it all came from one address in the University of Toronto. So my guess is it's probably a student project that went wrong. Maybe Mr. Spock happened to spend some time in Toronto back in 2008. When I was doing this analysis, Ray Bellis tipped me off about a DDoS attack that was going underway at that particular point for the 2013 DTL exercise. And he suggested having a check to see if this particular pattern was found of the DDoS attack, if it had been found in the DTL data. So I'm very grateful for Ray for giving me the tip off about that. As it turned out, didn't appear to be an issue. None of the traffic there seemed to match the pattern or the footprint of that particular DDoS attack. So the result of my findings and analysis of all that is there's a lot of RD1 traffic going through the route already, round about 12%, but it varies from year to year. I think it's 15% plus or minus 5%. I've seen it as high as 20% in 1 year of the overall route server traffic has RD1 bit set on it. And other years it's maybe as low as 10-12%. So it's probably always going to be that way and is never going to change. And that pattern behaviour doesn't appear to be breaking anything significant. Any of these naive resolvers that are making these queries with RD1 bit set, they're either failing safe or they're working around those referral responses in some other way. It's not causing the sky to come in, we're not having any alarms going off, we're not seeing software failing, so it doesn't appear to be creating any problem. And we're getting billions and billions of those referral responses coming back from the common net, from the root servers to ComNet and ARPA addresses from these naive clients. That doesn't appear to be causing any great problem in the network. So therefore I think it's reasonable to assume that the strategy that ICANN's proposed by having delegations of these TLDs and have the delegated name servers return NX domain is not going to cause any significant problem. In addition to that, the actual volume of RD1 queries that are seen for these new JRTDs is much, much, much lower in absolute and relative terms. We're talking just now that what I saw in the DTL data sets, query numbers in the orders of the thousands, whereas for the existing live TLDs like ComNet, the numbers of the order of the billions. So whatever's going to be generating those existing requests for gTLDs should be able to cope with those referral responses. And even if they can't deal with it, we're talking about a very, very small problem for a potentially very small number of clients, and it doesn't look like that this is going to cause any great trouble. An issue might be that the stuff for .mail, that could potentially cause that mail gets blocked or bounced, but in actual fact what's happened since then is ICANN has decided, thanks to the advice from SAC, the Security and Stability Advisory Committee at ICANN, that .mail is also going into this leopard colony along with .home and .corp. It's too dangerous to delegate. So we don't really have to worry about .mail from that point of view anyway. So even if there was a theoretical risk, that risk has now been obviated by another strategy. So the ultimate conclusion from that is that ICANN's name blocking strategy shouldn't cause harm, but on the other hand, I think it would be nice if ICANN had commissioned the research to actually go and do that analysis before they announced that particular name blocking strategy. They did the strategy and then someone came along afterwards to them, like myself, in this case, to try and verify if that strategy was sound or not. And I think that's perhaps doing things the wrong way around, but hey, this is ICANN, strange things happen. With that, I'm done and I'm happy to take any questions.
David Friedman, Clarinet. Are these new gTLDs we should register?
Sorry?
Are these names,
yep,
gTLDs, that will be blocked from being created?
No, essentially none of the gTLDs are going to be blocked. Essentially what ICANN has said is that corp, home, and mail are going to be put into special measures, which essentially mean they'll probably never ever be delegated. They're only going to get delegated if the holders of those domains or the successful applicants for those domains can guarantee it's not going to cause any harm. So until those applicants can prove that, ICANN's minded not to delegate those 3 particular TLDs. For all the others, they're going to go ahead regardless. Some of them are going to be in this low-risk category because they had less than 50,000 queries per day. In the DTL data, they were considered low risk, and they don't have to go through this controlled interruption mechanism that was discussed with NX domain responses and all the wildcarding. It's the ones in this middle category are the ones which have to apply these special measures or different measures, which means, again, for risk mitigation. But in my opinion, the fact they're doing this blocking and based on purely the names and the frequency of these names appear in the DTL data is an unsound strategy, and I'll tell you why. The first reason is we're looking at DTL data, which is essentially 1 day's worth of traffic. So how do we know that data is representative of what really goes on in the internet all the time? We don't. But we can't get a better data source than data. It's just impossible to log all the traffic for all the root servers and analyse it. There's just far too much data. It can't be done. The second issue I've got with this thing is there are other patterns of behaviour that were found in the initial study that looked at other things that could be a more serious problem. For example, the MX record traffic and the SRV query traffic, that indicates things have been misconfigured and they're looking for traffic. That could also be a concern. Likewise, concerns over things around Active Directory. And I would have thought those have been measures that perhaps should have had more emphasis than ICANN has decided to do, but that was ICANN's choice, not mine.
Okay, thank you.
Okay.
So, Mark McFadden, Interconnect Communications. I have a question about your leper colony. RFC 6761 gives us a way to reserve.
Yeah, but again, this is the other problem. This is locking the door after the stable horse is bolted. Yeah, we're trying to set aside.
I actually came to the microphone with a question, but now I have a comment.
Okay.
I think if the DTL data is all that you have,
yep.
Then at least some of the decision making is data driven. It's all that you've got to work with.
That's right, but in some cases it's been data driven after the fact. For example, this issue about naive query stuff. ICANN had no data on that at the point where they decided this is what a risk mitigation strategy would be. They had no data on that, and they didn't commission any study into that. They just decided that's what we're going to do.
Okay, let me buy you a beer, and I'll debate you on that
topic.
Topic.
Yes.
We shouldn't do that in front of the crowd. But your work, your research is far more interesting in a way, in that it might actually lead one to think that there were other strings that we should consider for 6761 style protection.
Yeah.
And so my question was going to be, when you looked through the data, were there other strings like that, or did you sort of have the same reaction that we had back in December when we looked at the DTL data?
Well, if you're talking about the number of, if you like, TLD strings, the concern is that was actually done for the initial ICANN study that was presented at the UART meeting last year and at the ICANN meeting in the summer of last year too. There are no other significant strings. We counted all of the TLD strings and all of the queries in the DTL data sets for 2012 and 2013, and we presented all of that information. So as far as I know, there were no other significant strings that had a high instance over and above the ones that were already mentioned. So I don't think there's any other strings in there that would be considered appropriate for an update to that particular RFC mark.
And so while I accept your point about the horse being gone after the door was closed, I accept that. The current internet drafts that are out about reserving strings using RFC 6761 actually use that research as their reason for reserving the strings.
Yeah.
Okay.
Jim, one of the strings that's been topical the last week or so has been .prod. This probably was way below the thresholds that you were looking at, but I'm wondering that since it's topical, would you care to make any comments about it?
The short answer to that is no, because I've really not been too concerned about this gTLD thing, and my focus has been elsewhere for the last few months. Off the top of my head, I can't remember where the query rates for .prod were, but if someone wants to ask me about that, I've got the data and I can find that out. So I really have no comment.
Great, thanks.
Okay, thank you very much, Jim.